Mohammad Siddiqur Rahman. Today I'm just recording my understanding about assignment number 8 of behavioral learning. So it is a special type of imitation learning that train an agent to mimic the behavior of an expert. So apart from the traditional reinforcement learning, which requires 100 millions of interaction for the agent to decide this action, behavioral learning actually allows to learn the agent with a smaller data set from an expert demonstrations. Here we are going to implement the Honda driving data set to control the steering wheel. So this is from an autonomous vehicle. So for this, we have to import some library function from PyTorch and the driving dataset of sample images for training purpose, and we also use that for training the agent and also for the prediction of the images. So for this, first we're just loading the dataset into our CPU, and there is a CNN model. There is actually 66 by 200 pixel RGB images, and that will be first normalized. And there are 5 filters of different kernels. There will be 5 and 3 by 3 kernel. These are the hidden layers. And after 5 hidden layers, we're applying flattening layer that will convert all the neurons into one big array. And finally, we are just using 3 dense layer that is called fully connected layers of different neurons. And finally, the output is only one. It is the control of the vehicle in the steering wheel. So this CNN architecture has about 27 million connections and 250,000 parameters. So we're going to develop the model from NVIDIA. It is from auto driving. So at first we were just loading this, and as I mentioned earlier, there are some convolutional models. It is there. So conventional models of convolutional feature maps. It is first is for 24 filters and 36 filters, 48 filters. These are the uh, neurons from here of different kernels, 5 by 5, 5 by 2 by 3, and so on. After that, we're just passing through it to a platinum layer. So everything is converted in a 1D array that is 64 by 18. After that, there are 3 dense layers of 100 neurons to 50 neurons conversion. Then second neuron is 50 neuron to 10 neuron conversion. And finally, it is 10 neuron to 1 neuron conversion, which is the output. So we're just refining the normalization values. So we're just dividing by 157. That is to normalize all the features variables. And we're just applying the value distribution function to all the layers. Now it is all the model architecture. Now we are just trying to train. So for training purpose, we're setting the size is 256. Also this size is 256. We'll run this training for 50 epochs with learning rate 0.001. So now the first thing is we have to initialize the model and we have to train the model with optimizer. And here we use Adam optimizer. So these are the functions to load the NVIDIA model, and the optimizer will use Adam. And for loss function, we'll use mini square error because it's a relation problem. So we're just loading the sample images from split it in tuning and testing set. So here you can see that is 10,000 training images of 66 by 200 pixel. This is an RGB. That's the channel is 3, and the test image we'll just train it with. We'll just test it with 1,000 images. So these are the sample images of steering angle. This is nothing with the control. So here now we'll just train the model into the agent. That is, so we're just loading the model to a device and just training it. And for loss collection, we are just defining this variable, and we'll just find the best loss after each epoch. We'll just start training from here. So at first, we're just loading the data, and that is the input batch, and this is the target batch, and this is the ground truth. This is the actual value, and we're just loading the input batch from the set to our device, and also our target load device, and we're just just applying our optimizer function, which is add-on function, and we're just after optimizing, we're just taking the input as output, then we're just started to find the predictions for training variables, and we're just getting the loss functions where it is the from the difference of outputs and the target batch, we're collecting the loss functions. And here is a way to give to go one back version step, then and optimize the step. Finally, we're just taking all the loss functions, convert to NumPy, and just make all the losses here. So we can also calculate average batch loss size, that is the total batch loss but length of the training set, and we can print it. So for each epoch, for each training, we're just calculating what is our present loss function is less than previous loss functions, and if it happens, we'll save the model and we'll just print it. So here, so that is after 50 epoch, the loss is gradually decreasing. We're saving the new BIS model. Finally, we see that our final model, our final batch loss ended up to 0.186, and total training time is 919 seconds. So if I plot this and the loss function against each epoch, we'll see that finally in the progression of the higher epochs, the total mean square error is decreasing, so that our new model got more accuracy and it is being saved. So now what we'll do, we'll just pass the test input to the model and verify the prediction whether it is matching with or not. For that, we're just giving the ground truth test set as the actual test output values, and we'll do some predictions. And this is exactly the same codes line that I explained before. But the thing is, we need not use gradient calculation here because it will no longer use the back propagation. And we're not using the optimizer. That's why it will reduce the memory consumption and speed up computation. That's why we don't need we have disabled gradient calculation, and we don't need optimizer here. And we're just in the selections, and we're just calculating the loss, and this is the best loss of batch loss, and we're just calculating average loss. So, and here you can see that the average loss is 0.290, which is just like our training data set. Training loss, that is 0.186. Now it is 0.290, and you can indeed verify that is the truth values and prediction values pretty close. But it is see, if I tell about the performance, the performance is not up to the mark, that much good, but the performance could be improved if we would use a large data set, and we could here the training was done within 10,000 images. But if it could train with more images, then the training would be better, and the agent could get the best model with lower loss, and also for the test data set could predict the input values in a right way. So here you can see that there is a bit difference between the input training angle and prediction angle. If it could be modeled or trained with a higher large data set, it would be more better. So that's all the things about behavioral cloning. That is the agent does not take the whole data set to train the agent to decide the best steering angle, rather than it just allows to use a lower data set, can very quickly learn the learn that is what should be the best model from an extra demonstration. So that's the advantage of use behavioral cloning, reinforcement learning.